Hello, we are continuing our conversation about stereochemistry, and this lecture is called Stereochemistry II. If you remember yesterday, we had just finished talking about how to identify whether a molecule is chiral or achiral. And remember, the trick was to spot a chiral compound, look for a carbon with 4 unique attachments. If you've got that, then you've got a chiral molecule most of the time, although we will see one sneaky exception towards the end of this lecture to when that is not true. I hate those exceptions, but that is in fact the case. So I want to talk a little bit more about enantiomers and drawing enantiomers. So let's say I ask you to draw for me some enantiomers. There's actually 2 ways for you to do that. So let me give you a molecule here. And we'll do like this. So it'd be great if you're copying this molecule down on your piece of paper with me here. Okay. And there's 2 ways to draw enantiomers. The first way is just draw a little mirror here and then just kind of draw the mirror image like what you would see of the reflection in the mirror. Everything's exactly the same, it's just sort of mirror image flipped. And so that little dotted line there is representing the mirror that's there. So if I gave you this and asked you to draw the enantiomer, you could just give me this. Now that's the first way to draw the enantiomer. The second way to draw the enantiomer is by doing a flip on all the wedges and dashes. So that's the second way. So I'll just go, this is way number 1. Oh no, this was way number 1 was the mirror. And this will be way number 2. The second way you could draw the enantiomer. Either way is totally valid, whichever one you prefer. Just flip all the dashes to wedges. So instead of being a dash there, I'll make it a wedge there. And boom, we've automatically got our enantiomer. So either way, either draw the mirror image or flip all the wedges and dashes, that works. And one thing you can notice is that these compounds, this compound here and this compound here, are both representations of the enantiomer of this compound. Imagine you took this compound and treat it like a pancake. Do a pancake flip. So just flip it 180 degrees. If you flip this molecule like a pancake, it becomes the first way of drawing the enantiomer, which is the mirror image. Can you see how this nitrogen would flip over onto the left side, and then the wedge would flip over and become a dash? So that is a way that you can see this relationship, that this compound and this compound are actually the exact same compound, but this compound is a mirror image of those 2 guys. So you guys are pretty easy to convince because I just convinced you to draw meth. So you guys just drew meth. That's right, this compound is meth. See, when I told you to draw it, you guys just followed blindly, didn't even think about what you were drawing. So let's take a look here at this compound a little bit more closely. And it turns out that methamphetamine, which is an illegal drug, very bad drug, has a stereocenter. It's a chiral molecule. So this is one form of methamphetamine, and there is another form of methamphetamine that looks like this. Okay. Now the form on the left is called L-methamphetamine, lowercase l. And the compound on the right is called D-methamphetamine. And it turns out that these compounds are enantiomers. They're non-superimposable mirror images of each other, and there is a chiral center or stereocenter right here on both of these molecules. You know this is a stereocenter because it has 4 unique attachments. It has a methyl group, it has this carbon, it has this nitrogen, and then a hydrogen that's not shown because it's an implicit hydrogen. And so it turns out that L-methamphetamine is sold in drugstores. It's totally legal. It's a nasal decongestant. I don't want to say it's harmless, it'll raise your blood pressure, but it is certainly not an illegal drug. The other compound, D-methamphetamine, is an illegal drug. The chemical has a high potential for abuse, it's addictive, and it can cause some pretty erratic behavior and just overall can ruin lives. So the government stepped in and said, you know what, D-methamphetamine, we're going to make that an illegal organic compound. That organic compound you can't have on your possession. But the L-methamphetamine, that actually has some medical uses. So it's interesting to see that just this change of a stereocenter can have a very, very big effect on the properties of the compound as it reacts with our bodies. So it turns out that our bodies have amino acids that are chiral as well, and so the interactions between molecules and proteins depend on chirality. So you can have a very, very different properties for a medication depending on which enantiomer that you are ingesting. Okay. Now, what do these D and the L mean? What do the D and the L mean? It turns out that that is an old school term. So D and L, so L and D, prefix is an antiquated term. Meaning we don't really use these distinguishing terms anymore. We don't use these prefixes anymore. And let me explain where they came from. So it turns out that chemists found out early on an interesting property about chiral molecules. Let me show a little cylinder here. And inside of this cylinder, I'm going to put some meth. A sample of meth. And I'll just draw this one as the one with the dashed line. Okay, it's just a tiny little sample in there. And then what I'm going to do is I'm going to shine plain polarized light at that sample. Plain polarized light means light of only one direction. It's passed through a special filter. So this is plain polarized light. So it's a form of filtered light, not that fancy. They just basically pass the light through a piece of plastic before they shine it onto the compound. And what they noticed was very interesting, is that the light was rotated a predictable amount. So from perfectly vertical polarized light, it was tilted a little bit to the left when they shine it through this molecule. And so this little angle here, they called theta. And they measured that angle and they thought it was interesting. And because it tilted to the left, they said it had a negative theta. The angle was negative. And so don't worry about any math here or anything, but the only thing important to know is that the light was rotated left. And that is why they called it L, because L is for left. Okay? So they noticed this interesting thing about chiral compounds is that they seem to rotate light. But it gets even more interesting. They took the same plain polarized light, and then let's do another tube of meth. I hope that your family members are not listening to this lecture. They may be wondering, what is this professor talking about? Okay, here's another tube of meth, and this time let's put the illegal meth inside the tube with the wedge line. Okay, there it is. And I'm not drawing in the nitrogen or whatever. It's just a simple representation of that meth. And then out the other end, the light gets rotated again, but guess what? It gets rotated exactly the same amount in the opposite direction. So now the light is being rotated to the right. And so this angle is positive theta. It's the exact same amount of rotation, just the opposite direction. So now the light is rotated to the right. And so this was abbreviated D for the Latin word dexter, which means right. So it's a Latin word dexter is where the D comes from. So what is the conclusion that we can make here? Is that enantiomers will rotate light but by the same amount but in opposite directions. And another important point to keep in mind is that there is no way to predict which way the molecule will rotate light just by looking at the structure. You have to do the experiment. You actually have to shine the light through the sample. You can't just say like, oh yeah, dashes always rotate light to the left and wedges always rotate light to the right. No, sometimes the wedge will actually rotate to the left. So the D and the L is purely experimental. You cannot look at a molecule and predict which way is going to be which. So cannot predict direction. Without testing it. But chemists have tested a lot of different molecules, and then you can look up in a book which way the light will rotate for a given compound. So what that means is if you gave me a vial of L-methamphetamine, the nasal decongestant, and a vial of D-methamphetamine, the illegal drug, I could figure out which one was which just by shining light through it. Just by shining light, plain polarized light, that filtered light, through that sample and seeing which way the light rotates, I would be able to tell you which one is illegal and which one is legal. Okay, so that's an interesting fact about enantiomers. Now, because we cannot predict which way a molecule will rotate light, to the left or to the right, it was decided that L and D is too inconsistent of a prefix term. We need a better way of naming enantiomers than L and D because we don't want to have to do an experiment every single time we want to name a chiral molecule. So it turns out those Cahn-Ingold-Prelog people figured out a way to name enantiomers as well. Remember that we use the Cahn-Ingold-Prelog rules to name alkenes as either Z or E. The same people are going to do the same thing, a similar thing, with enantiomers. So let's take a look at that on the next page. So we'll call this the modern way of naming enantiomers. Okay. And so let's start by drawing a chiral molecule for us to name. So I'll put chlorine here, put OH here, H in the back, and a methyl group on the left. Okay, so rule number one, step number one of naming using the Cahn-Ingold-Prelog rules. I'll just mention again, this is the SIP Cahn-Ingold-Prelog rules. Rule number one, assign priority to all four groups. Okay, so let's go ahead and do that. And remember, the priority is based on atomic number. The higher the atomic number, the higher the priority. So looking at our molecule, we can go ahead and quickly assign priorities. So chlorine has the highest atomic number of all the atoms connected to that central carbon, so it's going to get priority number 1. After chlorine comes oxygen, so that'll be number 2. After oxygen comes carbon, so that'll be number 3. And then the lowest priority, the lowest atomic number is hydrogen, so that'll be number 4. So again, assigning priority is just as simple as looking at the periodic table. Step 2, rotate molecule such that lowest priority group is dashed. So such that 4 is dashed. Now, we're lucky in this case, priority group 4 was already on a dash. But there'll be some times where priority group 4 is not a dash. So we'll need to potentially rotate the molecule, and we'll look at examples like that. But in this case, I already did I was nice, I already put the lowest priority group dash, and a lot of times that'll be the case. Step 3, connect 1 to 2 to 3. So I just take my pencil and I draw a line connecting 1 to 2 to 3. And can you see that it makes a circle? And can you see that the circle is going clockwise? If the connections are clockwise, we would call this R for rectus. Latin word. I think it means clockwise. And then if counterclockwise, we call that S, from the Latin word sinister, which means to the left. So it turns out that left-handed people were said to be sinister. I'm left-handed. I know, I'm so sinister. But it was believed that the people who were left-handed were like witches and stuff. So that's why today we use the word sinister to mean someone who's evil. But in Latin times, that just meant lefty, someone who's left-handed. Okay? So this molecule, since the arrows are going to the clockwise direction, this molecule would be classified as R. You would say the stereochemistry is R. All right, so now let's just do a bunch of examples of this, because this is kind of questions that I ask on exam. I'm going to give you a molecule, and I'm going to say identify the stereocenter as either R or S. So let's do some examples, and let's do a hard one. Okay, let's do this. Okay, let's assign this molecule as either R or S. So the first order of business is you have to identify the stereocenter. Where is the stereocenter in this molecule? It's right here. This is the carbon with 4 unique things attached to it. This carbon has hydrogen, chlorine, this carbon, and this carbon, which has 4 unique attachments, so it is a stereocenter. So now we just need to use the Cahn-Ingold-Prelog rules to determine priorities. So look at who's directly attached to that carbon. And so directly attached to this carbon, who has the highest atomic number? Well, we have a hydrogen, we have a chlorine, we have carbon, and we have another carbon. Don't worry about what's connected beyond. We just look for the immediate connections first. And based on the immediate connections, chlorine is number 1, for sure. And hydrogen is number 4, for sure, because it has the lowest atomic number. So now we just got to decide between this carbon and this carbon. And to break the tie, we do the same thing that we did back with the alkenes in the previous lecture. We make a list of all the atoms that are attached to that atom. So looking at this carbon, what do we have attached? We have an oxygen, remember double bonds count for that atom twice, and a hydrogen. So we would list it out, OOH. And then connected to this carbon, we have bromine, and then there's 2 implicit hydrogens not shown, H and H, and now we can choose our winner. Who wins between oxygen and bromine? Bromine has a higher atomic number, so even though there's 2 oxygens here, we don't even make it to the second option. We just compare the first 2, and we see that bromine wins. So what that means is that bromine is going to get, this carbon is going to be 2, and this carbon is going to be 3. So we've numbered 1, 2, and 3, and now we just draw our arrow connecting them. 1, 2, 3, and we can see that this arrow is moving in a clockwise direction. And of course we got lucky here in that the lowest priority group was already on a dash, so we didn't have to worry about rotating the molecule. We're moving in a clockwise direction, so this stereochemistry of this molecule is R. Let's do another example. How about this guy? Let's do one where the highest priority group is not a dash. And I'll show you a trick where you can get away with not having to rotate the molecule. Okay, let's go ahead and assign the priority groups attached to our stereocenter. So we know that hydrogen is going to be our lowest priority group. So we'll go ahead and give that a 4. And Chlorine is the highest priority group, so we'll give that 1. And now we've got a carbon here and a carbon here. Which one of these carbons do you think should be higher priority? That's right, this one here, because this carbon is connected to an oxygen versus this carbon, which is connected to carbon, hydrogen, hydrogen. So the oxygen is going to take out that priority. So this one's going to be 2, and this carbon is going to be 3. And now we're going to go ahead and draw our arrow connecting 1 to 2 to 3. And I can see that the arrow is moving in a clockwise direction yet again, but S is in front. So clockwise, but 4 is wedged, not dashed. So in this case, when the lowest priority group is a wedge instead of a dash, you just flip your answer. So don't worry about rotating the molecule, just rotate your answer in a sense, in that instead of, we would normally predict this movement to be clockwise, so R, but since 4 is wedged and not dashed, just flip your answer to the other one and make it S. Okay, so that's a nice trick, and then you don't have to worry about flipping the group. Sound good? Okay, well that's all well and dandy if the lowest priority group is a wedge. We already know what to do when the lowest priority group is a dash. We just do things normally. When the lowest priority group is a wedge, we do things normally and then flip our answer. But what happens if our lowest priority group is neither a wedge nor a dash, but it's a flat line? Well, let's take a look at an example of that. Okay, here we go. So let's go ahead and assign priorities. So our highest priority group is going to be the chlorine. That has the highest atomic number. Oops, not 4, 1. 1 for highest priority. Then comes fluorine, second highest priority. Then comes carbon. And then hydrogen is the lowest priority. Okay, now in this case, since the hydrogen is neither wedged nor dashed, we do need to rotate the molecule to get that lowest priority group in the dashed position. So just imagine we're on a merry-go-round and just move everything over 1. So the F will go where the H is, the H will go where the chlorine is, and the chlorine will go to the F, where the F is. So it's like being on a merry-go-round. I call this the merry-go-round method. So I'll just redraw the molecule exactly the same. I'll keep the wedges and the dashes in the same positions. I'll keep the line in the same position, and I'm just going to move every group over 1. So this is a rotation. This is just like doing a Newman projection rotation. Okay, so the H goes up to where the chlorine was, the chlorine goes up to where the fluorine was, and the fluorine moves forward to where the H was. And now this is the exact same molecule, just rotated. So I'll draw a little rotation arrow to show that. Now we can assign our priorities again. 1, 2, 3, 4. Now our lowest priority group is in the dashed position. So now we can just connect 1 to 2 to 3. We can see a clockwise movement. So this is going to be R. All right, how about one more example? Okay. Put a chlorine here. All right, so here's our stereo center right here. Let's go ahead and assign priorities based on atomic number. Chlorine has the highest atomic number, so it's going to get the 1. All right, and now we have an issue, is that we have carbons on the remaining 3 positions that are attached. We need to assign priority based on breaking that tie. Okay, so let's list out all the atoms that are attached. So we'll start over on this carbon here. We have bromine, hydrogen, and hydrogen. On this carbon over here, we have a double bond to carbon. So that's going to be carbon, carbon, and then there's also an implicit hydrogen on this carbon here to make the 4th bond. And then this position here has 1 carbon and 2 hydrogens attached. Again, we're looking at all the atoms that are attached besides the stereocenter. We don't count the stereocenter as being one of the attachments. We're just looking at branching outwards. Okay, so then based on these three atoms here, we can see that this carbon here wins because it's connected to a bromine, which has the highest atomic number, so that's going to be 2. And then between this guy and this guy, well, first round they tie again, so carbon, carbon. But then the second round, it's between carbon and hydrogen, so that means this guy wins over here. So this is going to be our 3, and this is going to be our 4. We'll go ahead and draw a line connecting 1 to 2 to 3, and we can see that that line is moving in a counterclockwise direction. But our lowest priority group 4 is wedged. So we need to flip our answer. So normally moving in counterclockwise would be S. But since our lowest priority group is a wedge, we need to flip our answer. So our answer will be R. Okay? So really, really important that we get a lot of practice doing this. And then there'll be a lot of that on the problem set. We'll do a lot of this during the live hours. It's so critical, and one of the most important aspects of organic chemistry is being able to assign R and S to a stereocenter. Cool. All right, so now I want to talk about a different type of stereoisomer. And so I'm going to kind of draw a little picture here. So imagine this is the universe of stereoisomers. It turns out that enantiomers are only a small subset of that. Remember that enantiomers are mirror image, non-superimposable mirror images. But you could have a chiral molecule that is not a mirror image. You could have a stereoisomer that isn't even chiral. We saw examples of stereoisomers like with those alkenes, but those aren't chiral. So we need a name for all the other types of stereoisomers that are not enantiomers, and we do. We have a name for those called diastereomers. Diastereomers. So let's take a look at some examples of what is a diastereomer. Okay, diastereomers. So these are stereoisomers that are not mirror images. And one thing interesting about diastereomers, enantiomers have identical physical and chemical properties. Although they maybe interact differently with our bodies, enantiomers will always have the same boiling point. They'll always have the same freezing point as each other. But diastereomers, they will have different physical and chemical properties. So let's take a look at some examples. Okay, so let's say we have this cyclohexane with a chlorine and a methyl. Now, to form the enantiomer, remember what we would do. We could either draw its mirror image, or we could flip all the wedges to dashes. But let's say we just flipped one of the wedges to dashes. So we'll take the chlorine and leave that as a wedge, but the methyl, we'll flip that one to a dash. Okay, well, those are definitely stereoisomers with each other. They both have the same connectivity of the atoms. The only difference is how they're arranged in 3D space, but they are definitely not mirror images of each other. So these would be considered diastereomers. They are stereoisomers, but they are not mirror images. So that makes them diastereomers. Another example is one we've already seen before. Here we have a Z-alkene, and compare that to the E-alkene. These are not chiral molecules because they have a plane of symmetry. Can you see where the plane of symmetry is for these molecules? It's flat, right along the plane of the page. So you could, because these molecules are planar, you could just slice right in between all the atoms and you would have a plane of symmetry along that axis. So because there's a plane of symmetry, these molecules are not chiral. They won't rotate light. They don't have any stereocenters. There's no carbons with 4 unique attachments. So these are not chiral molecules, but they are still stereoisomers because they differ only in the arrangement of the directionality of the atoms. So these would also be classified as diastereomers. And interesting to note here that the molecules do not have to be chiral to be diastereomers. Okay. So now you know what diastereomers are. So let me ask you a couple true and false questions similar to what I might ask you on an exam. True or false? If a molecule has exactly one stereocenter, it must be chiral. The answer is true. If you have a stereocenter, that means you have a carbon with 4 unique attachments. If you have a carbon with 4 unique attachments, you cannot have a plane of symmetry. So therefore, the molecule must be chiral. Here's another true or false. If a molecule has exactly 2 stereocenters, it must be chiral. So I'll just say if a molecule has, and I'm just doing the ditto marks to show that I'm just copying the same question. What do you think? If a molecule has exactly 2 stereocenters, it must be chiral. False. I can think of an example, and this is an interesting example, of a molecule that has 2 stereocenters, but also has a plane of symmetry. Let me show you on the next page. Let me show you on the next page. And this is, by the way, at the beginning of this lecture, I said there would be an exception where just because you have a stereocenter does not guarantee chirality, and I'm about to show you that exception now. Take a look. This molecule right here, it has 2 stereocenters. Take a look. Look at this carbon here. It has 4 unique attachments. It has a methyl group. It has an OH group. It has a hydrogen not shown because it's implicit. And it has this whole carbon thingy over here. So that's 4 unique attachments. Similarly, this carbon also has 4 unique attachments. It has a methyl group. It has an OH group. It has this carbon thing. And it has the implicit hydrogen not shown. So we have 2 stereocenters. There's no debating that. But I think you can see pretty clearly here, we have a plane of symmetry as well. Right down the middle. And remember, our definition of chiral means there cannot be a plane of symmetry. So because this has a plane of symmetry, it means it can't be chiral. Consider this. Let's try and draw the enantiomer of this compound. We would just flip all the wedges to dashes. This is the same molecule. This isn't actually any different. Same thing. Imagine I picked this molecule up from this side and flipped it over 180 degrees. Both of the OHs would become wedged because I'm flipping it 180 degrees, and then it's going to look exactly like the starting molecule. If you can take a molecule and flip it over and it's the same as the starting molecule, then that means it's superimposable on itself. It means that you can just flip the molecule over and it becomes the same molecule again. Remember, the definition of stereoisomers are they are not interconvertible by rotation. There's a special name for this type of molecule. It's called meso. This molecule is a meso compound. Okay. And some facts about meso compounds. It is achiral, and it's superimposable on its mirror image. And another interesting fact about meso compounds, they do not rotate light. All chiral compounds rotate light. Achiral compounds, including meso compounds, do not rotate light. So it's pretty easy to spot a meso compound. You're looking for a compound that has two stereocenters, but it also has a plane of symmetry. So that's how they're going to look in this class. So let's identify some meso compounds, because I can kind of hide it from you a bit. Take a look at this example. And this is hard. This is hard because it requires rotating molecules in your head, which is not easy. But if you look at this molecule, it appears to have two stereocenters, and it doesn't appear to have a plane of symmetry. I can't, if I draw a line here, it's not quite the same on both sides. I see Br here and OH here. That's not the same. I see OH and Br. Don't seem to be the same. However, imagine I rotated this carbon around 180 degrees. So rotate. This isn't changing the molecule. This is simply just rotating the molecule. It's not actually making a chemical change. We're not breaking or reforming any bonds. We're just rotating around that bond. So let's keep the left carbon exactly the same. But let's flip the right carbon 180 degrees. So if we flip the right carbon 180 degrees, the bromine is going to go up there, right? Because the bromine is going to basically swing around. And then the OH is going to swing around to this side, and it's going to flip from being a dash to a wedge. When you flip a carbon 180 degrees, you basically flip the dash to a wedge. And now you can see clearly there is a plane of symmetry inside. So because we found that plane of symmetry, this is a meso compound. Take a look at another example. What if I gave you the chair conformation? This is a chair conformation. I don't see any plane of symmetry here. It looks completely different. I can't seem to draw any plane of symmetry. But if we draw this as a flat structure, looking from the top down, you can see that we have two methyl groups both facing up. And once we draw that molecule, we can clearly see a plane of symmetry going right down the middle, meso. All right, here's another question for you. Okay, here's another cyclohexane. It's got two chlorines on it, both wedged. Is this compound meso? Well, sure enough, I do definitely see a plane of symmetry right here. So you might be tempted to say meso, but what is this compound lacking? It doesn't have any stereocenters, right? Remember, in order to be meso, you do need to have 2 or more stereocenters, and this compound has 0 stereocenters. Is this a stereocenter? No, it is not. Because if you look at this carbon, it has a chlorine attached, it has a hydrogen attached, an implicit hydrogen not shown, and then it has this carbon chain along the left and this carbon chain along the right. But look, the carbon chains along the left and right are identical. So this is not a stereocenter. It doesn't have 4 unique attachments. It only has 3. So this has no stereocenters. Same thing could be said with that other, this carbon down here. So no stereocenters. Not meso. Even though it has that plane of symmetry, we would just call this a chiral. Okay? So that's all the terminology, but here's the thing. I don't expect you from watching this video for this all to make sense. In fact, I expect after watching this video, you may be extremely confused. I've just set the rules. I've just set the ground rules. The only way that this is going to make sense is by doing tons and tons of practice problems, of which I'm going to give you many of them. So just keep in mind, if you're feeling overwhelmed, if this seems extremely confusing, that's normal, that's natural. This is one of the hardest topics in all of organic chemistry because we're having to basically think about molecules which are flat, drawn on the page, as existing in 3D space, and that is extremely challenging. But like I said, I promise, with a little bit of practice, you'll be assigning RNS with no problem. With a little bit of practice, you'll be assigning meso compounds, maybe with a little bit more trouble. But we will make it through this part of the class, even though I would say this is one of the hardest topics in the entire class. Okay, bye for now.